Hello everyone. Due to the request received from few students, I have prepared a video on mass transfer to give the overview on this module. Okay, that is the overview of the mass transfer. And okay, so let me share the screen. Okay, so mass transfer. So we know basically the flow of current is analogous to the heat transfer. The potential difference is responsible for the flow of current. That is the potential difference is the driving potential for the flow of current. And if we talk about the heat transfer, so the temperature difference is the driving potential for the flow of heat. That is the temperature difference is the driving potential for the heat transfer. Okay, and in the similar fashion, we can say the mass transfer is analogous to heat transfer. So the concentration gradient is responsible for the mass transfer. So we can say the concentration gradient is a driving potential for the mass transfer. So if we talk about the mass transfer, so what is mass transfer? Basically, if we consider a system that is made up of one or more components, so having the where we can say the concentrations vary from point to point. Okay, so there will be there will be a normal tendency for the transport of the different species from the region from the higher region, those having the lower concentration. Uh, Fine. So basically, we can say the process of this transfer of mass. This is due to the result of the species concentration difference. That is the concentration difference is responsible for this mass transfer. That means that there will be natural tendency for the transport of the different species from the higher region, that means the region having the higher concentration to the region having lower concentration. So few examples we can see uh, the refrigeration by the evaporation of the liquid ammonia in the atmosphere of hydrogen in the Electrolux refrigerator. Oh, that is the very, I can say, excellent example. Okay, that is the technical one. That is the in the uh, industrial uh, I can say the best example from the industrial point of view. The general example, we can say the humidification of the air in the cooling tower. So such type of examples where we can see the mass transfer. And we can see the mass transfer in day to day life also. We can say in the dissolution of the sugar added to a cup of coffee. That is the best and the simplest example that we can observe in day to day life. Maybe the transfer of the water vapor into the dry air. Okay, the drying and evaporation. Okay, so that these are the this is also one of the simplest example that we can observe in day to day life. Now if you talk about the modes of mass transfer. Okay, so basically mass transfer by the diffusion, the mass transfer by the convection, and the mass by the change. We have discussed mass transfer, very important to understand. Okay, so modes of the mass transfer. There are three different modes of. So we can talk about okay, let's discuss the first one, that is a mass transfer by the diffusion. So uh, that is also this mass transfer by diffusion is also known as the molecular or the eddy diffusion. Okay, so we can see. So what is the meaning of this? So we can say the transport of the water on this microscopic level as a result of the diffusion from the region of high concentration to the region of low concentration in a system, um, or we can say where the mixture of liquids or the gases is there, is called the molecular diffusion. So basically it occurs when the substance diffuses through a layer of stagnant fluid. Okay, stagnant fluid is there. So basically this happens when the substance diffuses through a layer of stagnant fluid. And and maybe and this is due to the can be due to the concentration or the temperature or the pressure gradient. And if you talk about the gaseous mixture, so the molecular diffusion occurs due to the random motion of the molecules. And if we talk about the turbulent motion, so we can say one of the diffusing is in turbulent motion, and the eddy diffusion takes place. Okay, so this is this condition we can see when one of the diffusing fluid is in turbulent motion, so the eddy diffusion takes place. So we can say this mass transfer will be more rapid by this eddy diffusion as compared to the molecular diffusion. Now the second one is the mass transfer by convection. So the mass transfer by the convection involves the transfer between a moving fluid and a surface, or we can say or between two relatively immiscible moving fluids. The example can be the evaporation of the some chemical like the ether. Okay. Now the next one is the mass transfer by the change of phase. So here so let's see what is the meaning of this. So mass transfer. So this mass transfer by change of phase means it occurs whenever a change from one phase to another takes place. So we can say the mass transfer uh, occurs due to the simultaneous action of the convection and the diffusion. So the examples can be mixing of the water vapor with air during the evaporation of water from the lake surface. Okay, or we can say the boiling of the water in the open air. Okay, and we can say the hot gas escaping from the chimney rise by the convection and then diffuse into the air above the chimney. Okay, so such type of examples. Okay, so these are the modes of the mass transfer, very important to understand. And now the another term is which is required is the concentration. And the concentration, so here if we talk about this concentration, so the molar concentration, okay, so the mass concentration, molar concentration, mass fraction, mole fraction. Okay, so such term arises, so that already very well explained in okay the notes. Now after this, the velocities, that is also important to understand, and then the fluxes. So that is required to okay, that is required for solving the problem. In fact, in some problems it can be asked. Okay, now okay, so after this, let's see the Fick's law of diffusion. It is the most important law as far as the mass transfer is concerned. Okay, very important to understand. And okay, so let's see about this Fick's law of diffusion. So basically, we can say let's understand this. So basically, in order to understand this mass diffusion, uh, uh, we can take this such type of system where uh, a transport process or okay originating from the molecular activity. Okay, this we have to focus on this process, a transport process that is originating from the molecular activity. Okay, so we have to understand first the mass diffusion. So let's consider the chamber. Okay, we have considered a chamber in which two different gas species uh, A and B at the same temperature and pressure are initially separated by a partition. Okay, you can see initially separated by the partition. uh, okay, the left compartment has a higher concentration. Okay, that is we can say higher concentration means the more molecules per unit volume, okay, of gas A. Okay, whereas the right compartment is rich in the gas. Okay, is rich in the gas. Okay, now we can say when the partition wall is removed, a driving potential comes into existence, which tends to equalize the concentration difference. So the mass transfer by the diffusion, okay, takes place in the direction of the decreasing concentration. Okay, and uh, we can say there will be net transport of the species A to the right, okay, and of the species B to the left. So after, we can say, after the considerable long period, the equilibrium condition occurs, and that is the uniform concentration of the species A and B will be achieved, and then the mass diffusion will stop. So okay, so we can observe this through the experiment, that the molecular diffusion is governed by the Fick's law. Okay, so that can be expressed by this expression, Na is equal to, okay, Ma divided by A, and it is equal to minus DAB. Okay, this dCi by dx. What is the meaning of this? So basically, Ma represents, okay, this Ma represents the mass flow rate of species A, okay, by the diffusion in kg per second. A represents the area through which the mass is flowing in meter square. So Na represents, just give me a minute. So what is the meaning of this Na? So Na represents the mass flux of a species A, okay, and the unit will be kg per second meter square. Okay, kg per second meter square. This will be the unit, or we can say the kg mole per second meter square. Okay, so the unit is this. I will write here the kg per second meter square, or we can say the unit will be kg mole per second meter square. Okay, now the DAB represents the diffusion coefficient or the mass diffusivity. Okay, and the unit of this DAB is meter square per second. So what is this diffusion coefficient? We can say, if I'm saying, okay, this diffusion coefficient is, we can say, the unit of this mass diffusion coefficient is same as the thermal diffusivity, that is a meter square per second. Okay, and or we can say it is same as the kinematic viscosity also. So the diffusion coefficient is a transport property of the fluid. Okay, since it is having the same uh, unit, or okay, or dimension. So we can observe this, the concentration of species A. Okay, see the concentration of species B. This shows the mass transfer by diffusion in a binary gas mixture. So we can say here, as far as I've written here, the Ca represents the concentration or the molecules per unit volume of species A in kg per meter cube. Okay, this is Ca. This is Ca will be in the unit will be kg per meter cube. Okay, and what about this term dCA by dCA by dx? This term. This term is the concentration of the gradient for species A. Okay, so this will act as a driving potential. Okay, so that is also that is the unit is in kg per meter cube. Okay, that unit. So okay, so if I talk about this for the mixture B, so I can write the equation like this: the NB is equal to MB by A. Okay. Now in the, okay, so I can write like this. This will be equal to minus dBA into dCB divided by dx. Okay, so we can observe that the diffusion coefficient D, that is DAB or DBA. In this case, it will be dependent upon the temperature, pressure, and the nature of the components of the system. Okay, so we can see here this Fick's law of diffusion is analogous to the Fourier's law of heat conduction and the Newton's law of viscosity. Okay, so we can say here this if I talk about the Fourier's law of heat conduction, so it is equal to Q is equal to minus K dt by dx. If I take A here, so I can say minus K into dt by dx. Okay, so it is on this Fick's law of diffusion is analogous to Fourier's law of heat conduction as well as the Newton's law of viscosity, that is tau is equal to mu du by dy. Okay, so we can say after comparing these equations, we can find that the Fourier equation describes the transport of heat energy due to temperature gradient. The shear equation describes the transport of momentum due to this velocity gradient. While the Fick's law describes the mass transport due to the concentration gradient. Okay, so this you can see this concentration profile. Okay, you can see the variation of this concentration profile. Okay, so the detail I've already talked well in detail. Okay, that's also already provided to you. Now, now let's come to this general mass diffusion equation in the stationary media. Okay, so this equation is similar to the three-dimensional general heat conduction equation in the Cartesian coordinate. Okay, so in the similar, I've already told you this heat transfer is analogous to the mass transfer. Okay, so so we can say so in the similar fashion as we had derived the equation for the three-dimensional general heat conduction equation in the Cartesian coordinate, we can derive the equation for this general mass diffusion equation in the stationary media. Okay, the concept is same. Okay, so this is very well explained in the notes that I've already provided to you. Okay. Now you can see so basically this we had discussed during the conduction in module 1, the three-dimensional general heat conduction equation, the Cartesian coordinate. So in the entire concept is same. In the similar fashion we can derive the equation for the general mass diffusion equation in the stationary media. And in that first module itself, during the conduction, we had discussed about the heat transfer through the cylinder, heat transfer through the plane wall, the cylinder, and through the sphere. Okay, and the heat transfer through the composite wall, composite cylinder, and the composite sphere. Okay, so in the similar fashion, we can formulate the problem. Okay, and we can derive the expression for this mass transfer through the uh, plane wall, mass transfer through the cylinder, mass transfer through the cylindrical shell. Okay, in the similar fashion, we can derive the expression. Now after this, okay, so let's see the problems. Okay, so how can we solve some problems on this? Okay, the mass transfer. So just go through this problem. Okay. Read this problem. Okay, so in the here the hydrogen gas at 25 degrees Celsius and 2.5 atmosphere. Okay, so this flows through a rubber tubing of this the 12 mm inside radius and 24 mm outside radius. Okay, the binary diffusion coefficient of hydrogen is given this value. Okay, this is the value, and the solubility of the hydrogen is this of the hydrogen per meter cube of the rubber at 1 atmosphere. If the gas constant for the hydrogen is this and the concentration of the hydrogen at the outer surface of tubing is negligible, now we have to calculate the diffusion flux rate of hydrogen per meter length of the rubber tubing. Okay, so let's solve this problem. So we can say, first of all, we should write what is given in the problem. So the given is the pressure is given, that is 2.5 atmosphere. So So okay, so let's convert this into in the Newton per meter square. So we'll multiply by 10 to the power 5. So this is in Newton per meter square. Now the radius is given as inside radius. So R1 is 12 mm. So it is 0.012 meters. Now the outer radius is 24 mm. So 0.024 meters. Now the temperature is given as 25. So we have to convert this in Kelvin. So 25 plus 273. So it is 298 Kelvin. Okay, and okay, so let's solve this. So we have to find the diffusion flux rate of the hydrogen per meter length of the rubber tubing. So let's see. So first of all, we'll write the equation for the perfect gas law. We know P is equal to mRT. Okay, so from this we can write M is equal to PV by RT. Okay, that is nothing but the concentration. So we know the value of P. We can write this P. The value is 2.5 into 10 to the power 5. This okay, so we'll put the values. So gas constant value is given in the problem as 4160. Okay, the joule per kg Kelvin. This is given in the problem itself. Now they put the value of V. Okay, so just put all these values and then we will be able to calculate this. So let's do it. Okay, so we'll put the values. Okay, so first of all, okay, so this V is required. Okay, so for this we need to work. Though this R is given as this 4160 and T is 298. Okay, so we have to work for this factor, this V. So let's see this. The solubility. Okay, so we can say what we can comment on this. Okay, so we can say okay, we will calculate here the solubility of the hydrogen at the pressure of 2.5 atmosphere. Okay, so it is given as this 0.055 the problem itself. Okay, so this is okay, so solubility of the hydrogen at a pressure of 2.5 atmosphere is this. Okay, so this is given as 0.055 meter cube of hydrogen per meter cube of rubber at 1 atmosphere. Okay, so we'll multiply this by 2.5. Okay, so calculated value is 0.1375. Okay, meter cube per meter cube of rubber tubing. Okay, rubber tubing, and that is nothing, that is equal to the volume. Okay, volume of the hydrogen in meter cube per meter cube of rubber. Okay, so the value of volume is this one. Okay, 0.1375. So we'll put the value here. Use different 0.1375. Okay, so in the now we'll calculate this. The calculated value is this 0.0277. Okay, kg per meter cube of rubber tubing. Now the diffusion flux, we know the formula for the diffusion flux. It is equal to M is equal to D CH1 minus CH2, okay, divided by this delta X into AM. Okay, so now we'll put the value. So let's calculate this term one by one. What is delta? Is delta X is nothing but R2 minus R1. So we'll put the value. It is 0.024 minus 0.012. So 0.012. Now AM, we can calculate by this expression 2 pi L R2 minus R1 divided by natural log of R2 by R1. Okay, we'll put all these values. Okay, we know the value of R2, R1 and all, so we'll be able to calculate it. Why to calculated value is 0.1088 meter square. Now, okay, so now we'll put the value, the above expression. So the value of D, first of all, we need to put it. Put the value of this. So the D, the diffusion coefficient of hydrogen, is given in the problem itself. So M is equal to, it is given as 2.1 into 10 to the power minus 8. Now this CH1, so that we have already calculated this this okay, M is nothing but this is CH1. Okay, this is nothing but this is also known as this is CH1. Okay, that is equal to 0.0277 kg per meter cube of rubber tubing at the inner surface of this pipe. Now if we talk about the CH2, okay, so we have to work on the CH2. So see here, what about CH2? CH2 will be equal to 0. Okay, why? Because as the resistance to diffusion, okay, is given as the negligible at the outer surface of the tube. So CH2 will be equal to 0. Now we'll put the value here. So M is equal to this D value. We have already, I will put the value. It is 2.1 into 10 power minus 8. This CH1. We'll put the value, that is 0.02773 minus 0, and we put the value here, delta X, that is 0.012 into area, that is 0.1088. Okay, so to calculate okay, the answer is 0.528 into 10 to the power minus 8 kg per second meter. Okay, so this is the solution. Now let's see the second one. Okay, next problem. So the problems are very simple. This formula based problems are there. Okay, now let's see the next one. Okay, so read the problem. Hydrogen gas is maintained at the pressure of 2.4 bar and 1 bar on the opposite sides of a plastic membrane, 0.3 mm thick. The binary diffusion coefficient of hydrogen in the plastic is given as this, and solubility of hydrogen in the member is also given, kg mole per meter cube bar. Now calculate under uniform temperature condition of 24 degrees Celsius. We have to the following one, that is the molar concentration of the hydrogen at the opposite face of the membrane, and the molar and the mass diffusion flux of hydrogen through the membrane, that we have to calculate. So first of all, Let's solve this problem. So first of all, we will write what is given in the problem. So solubility is given, that is okay, the solubility is given 0.00145. The unit is mentioned here. Okay, I'm not writing the unit. Okay, the pressure, that is the pressure is given. Okay, that is 2.4 bar. Now the length is given, that is 0.3 mm, and the diffusion coefficient is given 8.6 into 10 to the power minus 8 meters square per second. Okay. Write the unit kg mole per meter cube bar. These are the unit. Now, okay, so let's see. So this C, okay, so molar concentration, the total pressure and the solubility. So the relation is the molar concentration is equal to this solubility into this total pressure. Okay, so here we'll write the value. So first of all, we'll calculate CH1. So that is this 0.00145 into the pressure, it is 2.4. So we can calculate the value CH2. Okay, that is 0.00145 into this one. So we can calculate the value. Okay, so here the calculated value is 0.00348 kg mole per meter cube, and here this the calculated value is 0.00145 and the unit is same. Okay, so this is the answer. Now the second, so we have calculated the molar concentration of hydrogen at the, okay, the first one. Second one, molar and the mass diffusion flux of hydrogen through the membrane, that we have to calculate. So the form, okay, the expression is NH is equal to MH divided by A, and that is nothing but this T times CH1 minus CH2 divided by x2 minus x1. Okay, so this is a mathematical expression, and that is nothing but this x2 minus x1 is nothing but L, so we can write D CH1 minus CH2 divided by L. This is the expression. We'll put all these values, and we'll be able to calculate it. So NH is equal to this D 8.6 into 10 power minus 8. This value is given, and then CH1 CH2 value we have already calculated. So we'll put the value of CH1 and CH2 here. The value is given. Okay, and okay, so I will just put all these values. Okay, so we will be able to calculate it. Okay, just put all these values, and the value of L is 0.0003. So we know the value of all. Just put the value, so we will be able to calculate it. So the calculated, the answer is this 58.19 kg. Write the unit kg mole per second meter square. Okay, so this is the unit. Okay, so now, okay, the next concept is this, the steady state equimolar counter diffusion. That is also a very, very important concept. Okay, it is okay, so required to discuss. Okay, so basically what is going on here, you can see, okay, this one, the chamber A and chamber B. Okay, so we can say the equimolar counter diffusion between the species A and B of a binary gas mixture Okay, so that can be defined as the isothermal diffusion process, in which each molecule of the component A is replaced by each molecule of this component B, and vice versa. Okay, so in order to understand it in the best possible way, let's consider two large chambers, that is chamber A and chamber B, connected by a passage. Okay, here you can see this is the passage is there, and this is the chamber A and chamber B, and connected by a passage. Okay, in such a way that each molecule of gas A is replaced by the molecule of gas B, and vice versa. The total pressure we know, this is P is equal to PA plus PB. Okay, so that will be the uniform throughout, and this specific concentration will be maintained constant in each of the chamber. Okay, now if we use this Fick's law of diffusion, so we can calculate this Na. We can calculate this Na. That is equal to Ma divided by A, and we can write the equation with the help of this Fick's law of diffusion. Okay, at the last we had derived this Fick's law of diffusion. Ppa divided by dx. Okay, at the last we have derived this expression in this Fick's law of diffusion. In the similar fashion, we can write the expression for Nb also in the similar fashion, where Pa and Pb represents this partial pressure. Okay, I will write this here, and B divided by A, so we can write minus PBA A divided by Dt into rate of change of this pressure P. So P and Pb represent partial pressure, Na and B represent the molar diffusion rates of the gases. Okay, of the species A and B. Okay, now the entire this derivation is there. Okay, regarding this partial pressure. Okay, so from this we will be able to generate the expression for this Na and Nb. Okay, final expression. So this will be here in dPa by dx. So finally we'll get Pa1 minus Pa2 divided by x2 minus x1. Okay, and here, and the rate of change of this partial pressure B, so it will be, this term will be equal to Pb1 minus Pb2 divided by x2 minus x1. Okay, so this generally uh, we can say in the distillation the two constituents whose molar latent heat of vaporization are essentially equal. So in this process we can observe this. So that's why I can say that it is a general practical example of this type of process. So let's take one more problem. Read this problem. Okay, so ammonia and the air are in equimolar diffusion in a cylindrical tube. Okay, the diameter and the length is given for the cylinder. The total pressure is 1 atmosphere and the temperature is 27 degrees Celsius. One end of the tube is connected to the large reservoir of ammonia, and the other end of the tube is open to the atmosphere. The mass diffusivity of the mixture is given. Okay, and the calculate the mass transfer rate of the ammonia and the air through this tube. So let's solve this problem. So here we can say this 25 okay, 25 meter length. So that means it is so let's talk about this, what is given in the problem. We'll focus on this first. Okay, so we can say this x2 minus x1. Okay, so this is equal to 25 meters. Now this Pa1 is equal to 1. Okay, atmosphere, so we can say If it is 1 atmosphere, so Newton per meter square, it will be 1.0132 into 10 to the power 5 Newton per meter square. Okay. Now, this is what? This is PA1. Now, we'll talk about this the second one, that is the PA2. Okay, we are talking about this equimolar diffusion. Na? Okay, now this PA2 is equal to 0, and here this diffusion coefficient is also given. Okay, that this mass diffusivity is given, that is 0.3 into 10 to the power minus 4 meter square per second. Okay, and then this T is given as this 27 degrees Celsius. So convert this in Kelvin. So it is 300 Kelvin. Now we have to calculate the mass flow rate of this ammonia. Okay, so let's see this. Okay, the mathematical expression is Na is equal to this dA divided by this GT. So it is, okay, the formula is PA1 minus PA2, PA1 minus PA2 divided by this X2 minus X1. Okay, now here we know this DAB is equal to DBA. Okay, so it is equal. So let's assume this as D. Okay, so we'll put all this value. So D, the value is given as 0.108. The area, pi by 4 D square. So pi by 4 into D is this 0.00. Just a minute. D, what is D? 3.5 mm. So 0.0035 square. Calculated area. Now G is what? Gas constant, so 8314 into this time. Temperature is this 300 Kelvin. So this, so the PA1, that is 1.0132 in 0. Okay, 10 to power 5. To 10 to the power 5 minus 0. Okay. Divided by 25. Put the value, we can calculate. Okay. Answer is 1.688 into 10 to the power minus 9 kg mole per hour. Okay, you can calculate this in meter square per hour also. Okay, so that value I've used here. Okay, that value is required to be calculated in meter square per hour. That is 0.108 meter square per hour. Okay, that value I've used here. Now, the molecular weight of ammonia and air, we know. Okay, the molecular weight of this ammonia is 17, and this air is 29. We can say the mass flow rate of ammonia, so that will be equal to 1.688 into 10 to the power minus 9, that factor. multiplied by 17, the calculated value, and the mass flow rate of this air, this value 1.668 into 10 to the power minus 9 that we have calculated above into 29, the calculated, you can calculate this. Okay, so this will be the answer. Okay, this fine. Now next problem. So this is an open tank, 5.5 meter in diameter. This contains 1 mm deep layer of benzene. Molecular weight is given as 78 at its bottom. The vapor pressure of this benzene in the tank is 0.13 bar. The diffusion of benzene takes place through a stagnant air film 0.8 mm thick. The system is operating at 1 atmosphere and 20 degrees Celsius. Under this condition, the diffusivity of benzene is this. Now, assuming the density of the benzene is 880 kg per meter cube, we have to calculate the time taken for the entire benzene to evaporate. Okay, so let's solve this problem also. Let's see what is given in the problem. So the mathematical expression for calculating this is, okay, so okay, here the values are given. Okay, so I'm not writing this what is given in the problem. Let's solve the problem directly. Okay, so you just mention what is given in the problem. Okay, I'm directly solving the problem. dA, okay, this capital M, okay, dAm DAMB divided by GT, okay, into P divided by x2 minus x1 natural log of PB2 divided by PB1. This is the mathematical expression. Okay, all the values are known to us. Okay, just I can say this. Let's see what is point is this. PB1 is 0.13 bar. PA1 is equal to P minus PB1. That is 1.03 minus 0.13. Okay, so in this way we can find this. Now this PA2 will be equal to P minus PB2. That is equal to 1.03 and this PB2 is 0. So we can calculate this. So I know this PA1, PA2. Okay, now all the values are known to us. Okay, this D value is given. This area I can calculate by this pi by 4 into this D square. Okay, I will write a small d because capital D is this diffusion coefficient. Okay, so small d I will use that is at the dimension. Okay, and all the rest of the values are given PA2. Okay, okay. Yes, let me correct this symbol. Okay, here in this expression, this is nothing but this is PA2 divided by PA1. Okay, not PB2 divided by P1. It is okay. The expression is PA2 divided by PA1. So this we have already calculated P value. We know x2 minus x1. We know A we can calculate pi by 4 D square. Okay, this D is known to us. This G2 is known to us. Okay, G is this. Okay, the value is 8314. temperature, this 20 and convert it in Kelvin, so 20 plus 273. Okay, this delta X, this value we know the thickness, that is 2.8 mm. So we will put all these values so we can calculate it. Okay, so just put all these values. So the calculated value is, answer is 0.03137 kg per second. Okay, now we'll calculate the mass of benzene. So it will be, let's calculate this one. So it is 5/4 d square. Okay, d is this. Fine. Now okay, we'll put this one. Okay, so density is given, so we'll multiply this one. Okay, multiply this one and convert this and okay, so convert this in meter. So we'll multiply by 10 to the power minus 3, 5.5 in mm. Okay, so convert it in meter. So then now multiply by density. So density is 880. Okay, in this way we can calculate the mass of the benzene. The calculated value is 20.91 kg. Okay. Now the time taken will be equal to this mass, that is 20.91. Okay, this time divided by this 0.03137, the calculated value that we calculated here. Okay, just we'll put all this value, so we'll be able to calculate it. Okay, fine. Yes, for calculating this, okay, this MB is 78. Okay, we'll put this all this value, so we'll be able to find this. The calculated answer is 666.24 seconds. Okay, so this is the answer. In a similar fashion, we can solve the other problem also. This the deep 30 mm deep. Okay, next problem. A 30 mm deep pan is filled with water to a level of 15 mm and is exposed to dry air at 40 degrees Celsius. Assuming the mass diffusivity as 0.25 into 10 to the power minus 4 meters square per second, calculate the time required for all the water to evaporate. Okay, in the similar fashion, we can calculate this. We can solve this problem also. This solution. Okay. So what is given? The given is this x2 minus x1 is what? This is 15 mm. So it is 0.015 meters. This T is 40 plus 273. So 313 Kelvin. This diffusivity is 0.25 into 10 to the power minus 4 meter square per second. Okay, so this is given. So I will apply the same expression that I had applied in this previous problem, and then we can easily solve this problem. Okay, so the rest of the procedure is absolutely same. So okay, for uh, okay, so we have to apply the same expression here. So, okay, so the water is diffusing into the air. Okay, so that we will apply the expression. It is CA MW divided by GT into P divided by x2 minus x1 into natural log of this PA2 divided by PA1. Okay, this is the expression. Okay, in the similar fashion, okay, Okay, the problem we had solved, the previous problem. Okay, in the similar fashion we can solve this problem also. Okay, we put all the values in the mathematical expression, we'll be able to calculate time required. Okay, so the final answer is 47.14 hours. Okay, so this is the answer. Now, okay, so we can say after this, so okay, so I'd given, I will talk about this, the okay, the this notes I'd given to you. Okay, so this here, you just see, I talked about here the mass transfer. Okay, is covered the mass transfer. Okay, so the modes of the mass transfer. Okay, the different examples of this mass transfer. Okay, today also I have discussed this. Okay, the modes of mass transfer, very very important. And now the important terminology, that is the concentration velocities and the fluxes. Okay, that is the this is the, I can say, the this is the mass concentration of the mass density. Is this the mass of component A divided by volume of the mixture, the molar concentration. Okay, so this is number of mole of the species A per unit volume of the mixture. Okay, it is also known as molar density. Now this, okay, this the next one. So this, okay, so this molar density, number of moles of the compound A divided by volume of the mixture. Okay, then this the number of moles of the component, we can calculate the mass fraction. It is the mass concentration of species A to the mass density of the mixture. Okay, now the mole fraction, the ratio of the number of moles of the component A to the total number of moles of mixture. Fick's law we have discussed. Okay, this is the, okay, you can see the detailed derivation is there. Discuss this well. Okay. Now, okay, description about the diffusion coefficient, mass diffusion coefficient. Now this the general mass diffusion equation that we discussed. The solution we can derive like three-dimensional heat conduction equation as the steady state diffusion through the plane wall. Okay, 1 minute. Okay, so the steady state diffusion through the plane membrane. Okay, very simple one. Plane membrane. Okay, like where they write for the plane wall. Okay, now the steady state diffusion through the cylindrical shell. Okay, the similar fashion we can make the analysis like we had done for the heat transfer through the cylinder. Now, fine. Now the steady state diffusion through the spherical shell. Okay, this we can do in the similar fashion as we had done for this heat transfer through the spheres. Okay, now the concentration, I have to calculate concentration distribution with the radius. Okay, so this, all these things. Equimolar counter diffusion that we have already discussed. Okay, today's discussion also. Okay, there is a derivation is there. Okay, now this another associated factor. Okay, so this okay, the diffusion through the stagnant gas Stefan's flow. Okay, the associated term. Yes. So this one, this the very important equimolar counter diffusion. Another associated concept, the diffusion through the stagnant gas or Stefan's flow. Now the, okay, now the, you can see the convective mass transfer, the mass transfer coefficient description about this. Okay, now we can see here the dimensionless parameters. Okay, so that is very very important. Okay, so we can see we have observed the things in convection. So in the convection, we had studied the different dimensionless numbers. It is very, very important in order to make the analysis of the convection. Okay, because the shape, dimension, orientation, and of course the temperature difference between the surface of the body and the surrounding fluid is very, very important factor. Okay, so these factors are expressed in terms of the dimensionless number. That's why the study of dimensionless number is very, very important for making the analysis of convection. Okay, so we can say in the similar fashion here in the mass transfer also the different dimensionless numbers are there, and these dimensionless numbers are very, very important in order to make the analysis of this mass transfer. Okay, so okay, most important. Okay, very for I can say for understanding point of view as well as for the examination point of view also. This okay, dimensionless numbers for the mass transfer. So we can see the first one is the Prandtl's number. Okay, so what is Prandtl's number? We know the Prandtl's number. Just give me. I will. Okay. Now you can see here this. Okay, the first one is the Prandtle's number. Okay, so this Prandtle's number you can see this. Okay, this Prandtle's number is the ratio of this kinematic viscosity to the thermal diffusivity. So basically, it forms the connecting link between the velocity and the temperature profiles. Okay, so these profiles, this I can say this hydrodynamic boundary layer thickness and this uh, and the thermal boundary layer thickness. Okay, so that will be same if when the I can say the Prandtle's number is equal to 1, then the hydrodynamic boundary layer and the thermal boundary layer will be same. We know this. Okay, so we can say it forms a connecting link between the velocity and the temperature profile, and these profiles, that is the velocity profile and the temperature profile, becomes identical when the Prandtle's number is equal to 1. Okay. Now the second number is this the Schmidt number. Schmidt number. Okay, so basically, okay, so this is the ratio of the momentum diffusivity to the mass diffusivity. Okay, so we can say okay, nu by d. So it forms the connecting link between the velocity and the concentration profiles. Okay, so these profiles show the identical behavior when Schmidt number is equal to 1. Okay, now the next one is the Lewis number. So Lewis number, it is the ratio of the thermal diffusivity to the mass diffusivity. Okay, fine. So it is alpha by D. So okay, so alpha by DAB. So we can say it forms a connecting link between the temperature and the concentration profiles. So these profiles become identical when the Lewis number is equal to 1. Identical when this Lewis number. And in the Schmidt number, this the profile show the identical behavior when the Schmidt number is equal. Fine. Now next one is the Sherwood number. Sherwood number, it is we can say it is analogous to the Nusselt number. Okay, in the convection heat transfer, it can be expressed as a ratio of the concentration gradient at the surface to the overall concentration gradient. Okay, so generally it is known as the mass transfer Nusselt number. Okay, concentration gradient divided by the overall concentration gradient. Okay, so generally you can see this expression hm divided by okay, okay, basically we'll get the expression like this. Schmidt number, the Schmidt number like this. Schmidt number is Schmidt number is equal to this HM x divided by D. Basically the function of this Reynolds number and the Schmidt number. Okay, function of the Reynolds number and the Schmidt number. So we can say about the Sherwood number. Sherwood number, it is generally denoted by SH. Okay, and so this mathematical expression x divided by D, it is a function of Reynolds number and this Schmidt number. We can say it is based on the analogy with the heat transfer. Okay, so basically some empirical correlations uh, are obtained under the different flow conditions. Okay, so it can be the flow over a flat plate, flow in the tubes. Okay, so general analysis in the mass transfer can be done as we had done for the convection, flow over the flat plate, flow flow over the flat plate, or flow through this cylinder. Okay, so this is okay. Now we can, I've already told you. Okay, so different correlations are there. That is the relationship between the dimensionless numbers for the mass transfer is there. Okay, so different correlations are there for the mass transfer also. Now the comparison between the Fick's law of diffusion and the Fourier's law of heat conduction. We can see, okay, so this the relay of difference, okay, if we compare this, so molecular diffusion is governed by the empirical relation in this mass transfer by this expression, and for the Fourier's law, this is the mathematical expression. Okay, now okay, we know the meaning of this. Okay, mathematical expression. So there is the difference in mathematical expression of the, and the second is the difference is negative sign here in this Fick's law indicates that the diffusion takes place in the direction of decreasing concentration, where in the Fick's law of diffusion negative sign indicates that the okay, heat flow takes place in the direction of decreasing temperature. Okay, so now this is Fick's law describes the transport of the mass of diffusion, while here Fourier's law describes the transport of the heat energy. Okay, and in the here the mass transfer stops when the concentration gradient is 0, and here in the Fourier's law the heat transfer stops when the temperature gradient is 0. Okay, so these are the major differences. Other differences are also there, so we can compare this Fick's law of diffusion with the Fourier's law. Okay, so I'd given the entire overview of this. Okay, so some numericals can be there for, okay, based on this dimensionless numbers also. Okay, so okay, in the similar fashion, so that is also this formula based. Okay, so some related numericals on this dimensionless number also required to be solved. Okay, so that's all from my side. So I've given the entire overview of this mass transfer. Okay, all the theoretical concept, and we have solved the number of problems also on this mass transfer. Okay, and I have taken the different problems here, and rest of the problems are already given along with the notes with the solution. Okay, so we practice this, and in case of any difficulty, you can ask. So thank you so much for watching.